So, hello everybody. Welcome to my talk. So, I'm Hendrik and I work for a company in Germany called the Rosen Group. We are here also a bronze sponsor at the conference, and you can check us out if you want. And at work, I work with C++20 and also in parts already with C++23, and we use all of the greatest and latest features of C++ when they become available. And I think that's not always the case for everybody who is using C++, and I think, therefore, it's a good idea to talk a little bit about my favorite features in C++ and in C++20, and therefore I came up with the idea to do a tour of what has changed with templates in C++20. And there's a lot of content in dedicated chapters, and at the end of each chapter there's a slide which indicates to you that now is a fine time to ask questions. But if you have questions in between, don't be shy, just shout out or raise your arm or make yourself visible or audible in any means possible. So then let's start. So maybe you are interested in following along now with your laptop, or you want to download the slides later. Then here you can go to this link, which leads you to the Google Doc, where you can get the slides from. But I think the slides will later on be also available via the conference. On some of the slides, you will find links to Compiler Explorer for the code examples, and you can try them out there as well. And on my slides, there's also code, and usually for brevity, I will leave out includes there, and of course, they are then there in the Compiler Explorer examples. As I already said, please ask a lot of questions. There are slides which indicates that you should ask questions now, but if you don't want to ask questions right now, you can approach me after the talk or in the coming days, or you can contact me, for example, on Twitter or on LinkedIn if you have questions or comments, and feedback, be it positive or negative, is also very welcome to the talk so that I can improve it for the next time I'm giving it. So then let's ask ourselves, what has C++20 ever done for templates? And the answer is a lot. And we have several big chapters here. The first chapter will be concepts. It's about half of the talk. So because it is like the biggest thing which has changed in C++20 about templates. The second largest topic would be non-type template parameters and all the changes around that, and a couple of examples what you can do with that. And then two more minor chapters would be templated lambdas and the relaxed mandatory usage of type name. And that will be it. And then let's start with the first chapter, which is concepts, and we will be looking at what concepts are and how we can use them in C++20 with concepts and constraints as constraints. So what is a use case for a concept? So we have a function or a class template, and we want to limit what the template parameters can be. And this is like a big sentence here, because if we use C++, it's already limited what we can use as template parameters because the code has to compile. And if we give our class template or function template the wrong types, then it will not compile and we'll get an error message. So that is already restricted. But maybe the error messages are ugly and buried in like 20 pages of noise. Could happen sometimes. And we can use concepts to make that more clear, what the requirements are for our templates, and we can also improve the error messages with that. But you can say that was already possible in C++17. We have tools to restrict template parameters. We have things like enable if, static asserts, type traits, void t. We can use all of this from our toolbox to already achieve the same thing. But concepts do it in a different way. They do it in a more readable way with possibly better error messages and a design of type constraints and type hierarchies which make sense. So we can build hierarchies of requirements as well, which makes more sense than before. And what we will not get is compile time improvements. There have been people around who have been doing benchmarks with concepts versus all the other stuff, and it's usually basically on the same level. Sometimes concepts are also a little bit worse in compile time. Then let's talk about what a concept really is. So A concept is a compile time predicate on template parameters. So we give it a template parameter and it maps that to a bool. Example would be, for example, here on the slides, we have stood forward iterator of t, and this is true if t is a forward iterator and false otherwise. They can, of course, take more than one parameter. For example, stood constructible from takes a type t and then variadic arguments args, and this is true if t can be constructed with these args and false otherwise. And usually these concepts are used together with constraints, and a constraint limits what types a template function class, a template function or class will accept as legal template parameters. The standard library brings a lot of concepts already shipped within. So we have usually 3 headers where we can find concepts in stud. So most of the concepts will be in the concepts header. And on the right-hand side, you see a screenshot of cppreference.com with a lot of the concepts which are in there. And these are the things which you would expect, something like same as, constructible from, derived from, etc. So the standard things you might need to check. There are also iterator-related concepts in the iterator header and ranges-related concepts in the ranges header. And of course, if you use third-party libraries, they will bring their own concepts with them. For example, if you have a look at ranges v3, this library brings a lot of concepts with it. So second thing is, what is the constraint? So how would we use a concept? So here we have a template function called norm, and what it basically does, it takes a vector of t values, it iterates over the values, squares them, adds them up, and returns this square root of the results, like a vector norm from linear algebra. And what we want to do here is, we want to give it a vector of things, but we want to restrict what these things can be using a constraint. And what we can use for that is a so-called requires clause, which here appears as the last element of the function declarator. And stood floating point is a concept from the standard library, and it is true if t is a floating point type and false otherwise. So here at compile time, it is checked whether our type t is a floating point type. If this is true, then this all would get compiled and the function is used. If this is false, then it might not compile, or it will not compile. You will get a nice error message that your constraint is violated. So these requires clauses can be used at every place where you can use concepts, so class templates, function templates, alias templates, whatever you can think of. In my examples, I will use mostly function templates for simplicity. And the last thing is, you are not required to use a concept here. In this requires clause, you can use anything which is a Boolean, which is known as compile time. So you could use a classic type trait here as well, or something else like a const expr bool, whatever you have. And now let's look at an error message we might get if we violate this constraint. So here's an error message from GCC when I try to call this norm function with a vector of stood strings. And what we get is, the compiler tells us we have an unsatisfied constraint, and that is floating point evaluated to false. And this is, I think, a pretty readable error message. It's not buried in pages of noise. Well, it's a simple template here. It would not be buried in noise anyway. But again, I find it quite a conceptually good error message. And if you have more complicated things, there's also compiler diagnostics to increase here the level of reporting you get from the concepts. So what are the details about the requires clause? So the keyword required is used to introduce the requires clause, and this is used to specify the constraints on a template function or class template. It can appear as the last argument of the function declaration. It can appear right after the template parameter list. And the keyword requires must be followed by some constant expression, which is bool. So it can be a concept, a type trait, whatever you like. And it can also be a logical combination of these things. So here in the last line, you see something like requires my concept of t and my other concept of t. And this evaluates to true if both of these are fulfilled and to false otherwise. I could also exchange one of these things for a type trait, for example, if I want to. So a lot of things are possible here, but the idea is to use concepts most of the time. So what happens now if we want to make our constraint for our norm function a little bit more complicated? So instead of having a std vector of t values, now I write it a little bit different. I have a template, and now it's const t reference values. And the idea is that t is now a container which contains floating points. And I can change my requires clause here to reflect that. So what I can require here is that our t has a nested member, which is a const iterator, which called const iterator, which is a std forward iterator. And I can, or I have to require, because I have this floating point check before, that we have a value type here, a nested type value type, which is a floating point. And I combine these with a logical AND. And this is a lot of stuff in a function declaration. It's really, really long and hard to read. And it's not necessary to write it this way. We could do it this way, but we can take all of these things here and put it into our own named concept and make it more readable and also reusable. If we wanted to use these at other places as well, we would need to copy and paste that, but by bringing it into its own named concept, we can reuse it, of course. Yeah, and how would we do that? So this is the definition of how we write a concept. We have the template keyword, a template parameter list, the keyword concept, followed by the name, which we give to the concept, and then a constraint expression. And a constraint expression can be another concept, a logical combination of concepts, and other Booleans which are known at compile times, like, for example, type traits. And it can be requires expressions, which is something which we'll see a little bit later, which is a way to build up concepts which do not relate to already existing concepts, but relate to something we invent. There are some pitfalls associated with this definition, so it's not possible to have recursive templates, so I cannot refer to the concept I write in its own definition, so this is not possible. And I cannot use requires clauses on concepts as well. So here I have a concept C2, which is something, maybe another concept or a type trait, and I want to constrain it with a concept C1. And this is not legal C++, and it's also not necessary, because what this code basically says is our concept C2 is something, which is here hidden by the 3 dots, but it also needs to fulfill C1. And for that, I don't need a requires clause here. I can just put an AND, a logical AND in there, and then C1 of T in there. So for that reason, we don't need that, and that's not legal C++. And that would be the common pitfalls. And as I said before, we can use also requires expressions to write concepts which do not relate to other concepts. And now we will talk about how that goes. We see here that the keyword requires is reused. It's used to start requires clauses, as we've seen before, but it also starts requires expressions. And a requires expression is something which evaluates to a bool and describes constraints on template arguments. And it's true if the constraints are satisfied and false otherwise. So the keyword requires then is followed by an optional parameter list, which is like in a function declaration, a comma-separated list of parameters. But these parameters are not real, so to say. They have no storage, linkage, or they have no lifetime, and they're only used as, let's say, an assistance in specifying these constraints. So we need here names for local variables of some types for some constraint checking later on, but they are not real parameters. They do nothing. They are just there for syntactic checking. And these parameters are in scope until the closing curly braces of the requirement sequence. And the requirement sequence is a sequence of requirements. It's aptly named. Each requirement ends with a semicolon, and there are several types of that: simple requirements, type requirements, compound requirement, and nested requirements. Each have their own slide later on. And what these requirements do is, these are the constraints which are checked on the template parameters and the local parameters. And therefore, they can refer to the template parameters, to the local parameters, and the parameter which are introduced in the parameter list, and to any visible declaration. And what happens there is, in each of these requirements, a template argument substitution takes place and syntactic checking of the code. And if these constraints are violated because there is, for example, illegal C++ code in there after template argument substitution, then this constraint will just evaluate to false. And if everything is fine after template argument substitution, it will evaluate to true. And this is done for every item in this requirement sequence. And the requires expression itself is true if everything is true, and if one of these items in such a requirement sequence would be false, then the whole requires expression evaluates to false. And here on this slide, we see a simple requirement. This is an arbitrary expression, which here is a plus b, for example, referring to the local parameters. And it's just checked that this is a valid expression. So here it is basically checked if a plus b can be added if they are of type t. And if this is the case, then this requirement would be true. And since it's the only requirement in the requirement sequence, the whole requires expression would be true. And if this is a named concept, and the only part of the named concept may be, then the whole concept would be true as well. The second type of requirement is type requirements. And it's started by the keyword, type name, followed by a type name, which can be qualified if you want. And the requirement is that this named type is valid. So for example, here we check if our type t has a nested type value type, and we check if our type t has a nested type size type. Now, if both of these exist, then each of these items in the requirement sequence would evaluate to true, and then the whole requires expression would evaluate to true. If only one of these exists, then this requirement would be true, the other would be false, and the whole requires expression would be false, because it needs to be both valid. Both needs to be correct in order for everything to evaluate to true. There are compound requirements, which are a little bit a generalization of the simple requirements, and it looks very similar. So we have an expression in curly braces here, which can be followed by an optional no-except qualifier, which can be followed by an optional type return type requirement, which is also a constraint, so here a concept. And this generalizes the simple requirement in a way that we can qualify it with no-except, and then we can check the return type. So what this translates to is we have local variables a and b, and the expression a plus b for type t must be valid, and it must be no-except, and the return type must be convertible to float. So this generalizes the simple requirement in that way. There are nested requirements, so I can put another requires keyword in there and then follow that by a constraint expression. But this is, in my opinion, not the most beautiful way of doing that. It has its use cases, but it's usually kind of ugly because you have a lot of requires here, and one can get really confused if you have a lot of requires, in my opinion. So, and coming back to our norm function from the beginning, where we had the requires clause with a stood floating point and stood forward iterator concept. Now we can, with the knowledge we've acquired now, put that into a named concept. So we call our concept iterable with floats because it fits on a slide. And we just combine stood floating point and stood forward iterator concept here with the end. And now it does what we want to do before, but we can now reuse it as a named concept, and our function declaration of the num function becomes much shorter because we just need to write requires iterable with floats of t, and this works. It's much more readable than before. We can reuse it. It does the same thing. But we can write it even in a more shorter fashion, so to say, because there's a shorthand notation. So instead of using the requires clause, we can get rid of the type name in the template parameter list and write our concept in there. And this is syntactically, or not, this is in its meaning equivalent to the requires clause we had before, but just shorter, and it's a question of taste, what you like more. The only thing which can confuse people is here if you have a concept which has more than one template parameter. So iterable with floats has only one template parameter t, and we can easily imagine that this is here done, what this means here. But what happens if we have a concept which has a lot of template parameters, like stood constructible from, yeah? From which side is the argument, are the arguments of the concept filled automatically? And if you remember how stood constructible from looked in the beginning, it stood constructible from t and then the args, then you can imagine that it's filled from the left-hand side automatically, also by this shorthand notation. But you need to remember that, and if you forget it, you can get confused, and it looks not so nice if you have here, if you had stood constructible from in there, then you have another set of pointy braces, and it's getting uglier to write it that way, and maybe then a requires clause is a more beautiful way of putting that into code. So maybe another example where concepts make sense and where we can use concepts from the standard library is, like, how do we do it if we, in C++, if we have a function which takes another callable as an argument? Usually we do it with templates. So we have a template with a type callable, our function called twice, which takes a callable and an argument, which is an int, and returns just the sum of calling it twice. So, and here it's pretty easy to see, but in a general case, it might be hard to estimate what the callable needs to be. Yeah? How many arguments does it take? What kind of arguments does it take? What does it need to return? Yeah? If you just have template type name callable, this is hidden away from you, and you have to look in the code to understand it. And again, since this is a 3-line example, this is easy to see, but imagine a more complicated piece of code where this could get hard to understand. And maybe it's a good idea to use concepts here to make it more understandable what we expect from our callable. And we could do that before C++20. There was another solution for that, which nobody likes, which is stood function. It does exactly that. It does more than that, but it documents what kind of callable we expect here, but it has a runtime overhead, and this is usually not what we want, at least in this case. This might be not what we want, and we want to do it with a concept. And the way we could do that is, again, building our own concept from concepts from the standard library. So there's a concept called stood regular invocable, which takes a callable, which I called func here, and arguments. So here I check whether func can be called with the argument arg. And I also use stood invoke result t to get the return type, and check whether with the same as concept whether this is the same as ret. So I can here build a concept which checks whether a callable func can be called with an argument arg and returns the return type ret. And this I can put into my call twice function with a requires clause, put the callable and the two ints in there, and I have achieved basically that kind of thing which I wanted to achieve with stood function before, without having a runtime overhead, because this is now only checked at compile time. And again, as you see here, I just again used concepts from the standard library and logical combinations thereof. And my main key point here is that you can achieve a lot by just using what the standard library gives you. You might come across only a few places where you need to write your own concepts using these requires expressions, because the standard library already has a lot. So next thing, we can constrain auto. Question?
Can you also use the requires expression and then use logical and, or should you use the requires in the requires?
You can do stuff like in a requires clause, requires, I don't know, concept 1 of t and concept 2 of t and even more. That's possible. You can also write an ad hoc requires expression. So we could write requires and then these other stuff from the requires expression. So you have a lot of freedom there. Was that the answer to the question? Okay, sorry. So where was I? Yeah, we can constrain auto. So everywhere we can use auto, we can put concepts as well and use these constraints. So we could write a function where the function arguments are constrained with a concept and also the return type. And this you can see as another shorthand notation for requires clauses if you want. I use that not that often because I find it rather ugly to write it this way, but this is also a matter of taste. If you like that, you can of course use it. And the next thing and the most important thing maybe with concepts is how do they change overload resolution? Because at the moment we only had ever one function template with one concept, and either it's correct and our code compiles or it's incorrect and our code breaks. But what if we have multiple function templates, for example? So what's happening is the compiler starts looking at the most constrained version of the template and works its way down to the least constrained or unconstrained version of the template, which means that in the end, we don't need to negate concepts if we want to have like two versions, like a constrained one and an unconstrained one. We can just write a constrained version of our code and then, for example, an unconstrained default version. So there's no need for negating concepts. And the other cool thing is a named concept can restrict other named concepts via subsumption, which means that if I have a concept which is concept A and then something else, and we have two function templates, one which is A and one which is A and something else, then the compiler can figure out that A and something else need to be picked, although the other one is also fulfilled, because it's A is fulfilled when A and something else is fulfilled. But we will see examples for that. And the overload resolution, as I just said, will prefer the concept that subsumes another, so which is more than just one thing. But there's a downside to that. This subsumption only works with named concepts and Boolean and logical combinations of concepts. So if you try to do the same thing with type traits, your code will break. That does not work, even though you're using requires clauses for that. And the concepts of the standard library are designed to use these subsumption rules. So let's look at examples for that. So this might not be readable at the moment. Am I in there? Yes. So here we have a concept A, which requires of our type T that it has a get function which returns a floating point thing. And then we have a concept B, which is A, and it also requires that T has a get special member function which returns a floating point. And then I have two function templates, one which requires A and one which requires B. And if I now call it with a struct which has a get and a get special function, then we see, okay, our concept A is fulfilled because it has a get function. And our concept B is also fulfilled because concept A is fulfilled, and it has a get special function. So both of these things are true. And what the compiler will now do is it will pick this overload here, so with B, because of the subsumption rules. B is A and something else. So B subsumes A, and this is picked, and the code will print hello from B. This is basically, I think it's better understandable with code than just with items on the slide. Second example. I have to move the mouse cursor over there. I'm sorry, I don't see where my mouse cursor is at the moment. It's there. So the setup is really similar than before. And the only difference is here. Now our concept B has changed. B is not A and something else, but B has the same content as A, but it's not referring to A anymore. And what now happens is our code cannot compile anymore. The compiler cannot know that we want to use these subsumption rules because we don't refer to A in B. We just do the same thing as A does, but we don't talk about A explicitly. So our code doesn't compile here. So if you want to use these subsumption rules, you have to make it explicit. You cannot just put the same content in the concept. Third example. Here again, it works again. And now concept A and B are completely separated. So concept A is only the get function. Concept B is only the get special function. And I have one function which is constrained on A. And I have one which is constrained via requires clauses on A and B. And now subsumption rules work again. The compiler can figure out, although both of these things here are true, that this needs to be picked because this subsumes A, and then it works again. And we get hello from B. And as I said before, it will stop working if you use type traits or anything which is not a concept. So here, I don't have any concepts anymore. I just have a requires clause with the stud is same v. And here, a requires clause with the stud is same v and something else. And this is true. This is true as well here for the example. And then we have ambiguous stuff and our code doesn't work anymore. So subsumption only for concepts, not for type traits and other things. If you have questions, it's a good time now because I have to close all these windows here. That's okay again. Yeah. Yeah. If you make whatever you use to make a named concept, that's not important. At least if you have a named concept in the end, and if you want to use subsumption, you have to make a relationship between two concepts. So one needs to refer to the other, like A and B, or I don't know, A and B and C, something like that.
What would happen if I had two functions where one requires A and one requires B, and A and B are completely independent of each other? So it's two overloads that could either of them could be satisfied. But they depend on each other and the concepts that depend on each other.
So you ask basically what if we have like a function overload and one has a concept A, one has a concept B. They are both fulfilled, but they're not related to each other in this subsumption way. Then you would also have like an ambiguous overload resolution and compilation will halt because this is very similar to the second example where the concepts were not referring to each other. So you need to make the relationship between the concepts explicit for this to work.
What would the error message look like if it's circular that ends up kind of the ones going around? Does it indicate that, or would it just you have to somehow work it out?
It depends a little bit. You will get, of course, in the beginning, this ambiguous overload resolution, and then it will tell you, well, this is picked, this could be picked, this could be picked, and usually then you would see in the function declaration the requires clauses, and then you would have to figure out that they are all true, but that's apparently visible. It depends also on the compiler. So if you, for example, use Visual Studio, the error messages for concepts are not that good. They are better for GCC, for example. And why is that? Yeah. So now overload resolution with standard concepts. Another example would be if we use something from the standard library, there's also subsumption built in. Here we have an overload resolution where we have an unconstrained function, one which is constrained using std predicate, and one which is constrained using std invocable. And just from looking at it, you may guess the relation. A std predicate is something which is invocable, which returns something which can be converted to bool. And a std invocable is just something which is invocable, and it's not cared about what the return type is. So in case you call it with something which is a predicate, then both std invocable and std predicate would be true, but the overload with std predicate is chosen. And if you call it with something which is not a callable, then the unconstrained version is chosen, and so on, so on. It's like the example before, but this is just to illustrate that the standard library uses very carefully the subsumption rules. And of course, you can have ambiguous overload. Here, for example, we have here std convertible to float and std convertible to double. And this can be both true, for example, if I call it with 5.0, and then the compiler doesn't know what you want, and compilation will stop. So you can use concepts in many places in your code, not only in these requires clauses. So concepts are booleans which are known at compile time. Yeah, so you can use them in const if, for example, or you can store them if you want and use them later on for whatever you want. So it's not something special which can be only used in requires clauses. Sometimes a question I get. And that brings an end to the first chapter. So concepts provide an easy-to-use functionality, constraint templates. We have an overload resolution mechanism based on the subsumption rules. And concepts from a standard library are good. Use them, and they take carefully, or they are designed carefully to take care of the subsumption rules. And I have time for questions now at the end of the first chapter. Yeah?
Can you combine concepts with logical?
The question is, can I combine concepts with logical OR? Yes, I can do that. I can use anything of the logical operators I want, and or not. Not is not very useful, because if you want to do like these overload things, you don't need not, but maybe there are some other places where you need not because you want to have like the exact opposite of a standard concept.
If that's the case, is there a way of retrieving which of the concepts satisfy within the function, for example? Or do you just have to retest them?
You would have to retest them. Yeah, you can just in your function, for example, call the concept again, store the variable, and use it in, I don't know, const if, or print it out, or whatever you want. Yeah. Second chapter would be non-type template parameters. And I'm deeply sorry, but I have to restart that again. It's not doing what I wanted to do. I wanted to do that. And I want to have that in front of me, so sorry. So non-type template parameters, this is a thing which we all know. It was fairly limited before C++20, so we could use integral types or pointers to member, enumerations, null pointer, and all of that. but there were a lot of things we couldn't use as non-type template parameters. And this has largely increased in C++20. So now we can use floats and doubles as non-type template parameters, and we can use classes and structs under certain conditions. So condition number 1 is the class must have either const expert constructors and destructors if they are user-defined, or if they're not user-defined, then only default constructor and destructor are allowed, so a literal class type, and only public non-mutable members and base classes are allowed, and then we call that structural types. And all of its members and base classes also need to fulfill these requirements. And if this is the case, then we can use our struct or class as a non-type template parameter. And this means, if you think carefully about it, we can use lambdas as non-type template parameters if they don't have a capture. If we capture something, then a lambda isn't a structural type anymore because the capture is handled like a private data member, and then that doesn't work anymore. So how would these structural types look? So for example, struct A with no user-defined constructor can be used as a non-type template parameter. If we have our struct A, which has a const expert and a non-const expert user-defined constructor, it depends which one of them we use if we give our type to the templated thing as a non-type template parameter. So it would be okay if it's the const expert constructor is used, and not okay if the other one is used. If we only have a const expert constructor, everything is fine. It can be used as a non-type template parameter. And if we have a private data member, like here with the private int a, then that's not okay anymore to use a as a non-type template parameter. And if our constructor is const expert, but we have a user-defined destructor, although it does nothing here, then it's also not okay anymore to use a as a non-type template parameter. So we have to be very careful what we can put in there. Yeah, we can use floats and doubles now in non-type template parameters. And if you think of it, that can be a little bit tricky because floating point mass doesn't behave like we expect it to do sometimes. And how does the compiler check, for example, if two floats and doubles as non-type template parameters are the same? And it's done by comparing the underlying bit pattern of the float and the double. And this can lead to problems, it's maybe a bit hard to say, but surprises if floating point mass is involved. So if we have a look at it here, so what I have here is I have a template, class template, which takes a double as a non-type template parameter. And now I check whether some of these instances of A are the same. So I have A of 1.0 and I have A of 0.5 plus 0.5, and this works out. And this works out in a lot of cases with multiplication, division, but you can construct cases where it doesn't work out because of floating point mass, because the results are not the same. So 0.3 is not the same as adding 0.1 3 times. So these are not the same objects here. As well as 1.2 minus 0.3 is not the same as 0.9. So these are also not the same type objects here. And unsurprisingly, plus and minus 0 are not the same because they're defined as different things in floating point mass. So that is maybe not so surprising. These can be surprising. But I don't know if it's, you have to be prepared for that, to encounter these things. Can I switch back here? No, I cannot. That's unfortunate. So as I said before, we can use lambdas as non-type template parameters. And since C++17, we can declare non-type template parameters with auto. And this is a way we can give lambdas to our class templates, for example. And if again, examples here. So if we look at that, we have a struct called thing, which takes a non-type template parameter func. There's a member function get, which just returns func of value. We create here a lambda calculator. We construct thing of calculator, and we can call the get message, and this works. And this is, I think, a really cool application of non-type template parameters. You can inject functionality into your classes with that, which changes. For example, I've seen examples where people used, like, for example, tax calculation in different countries where all the taxation rules are then into the lambda, and the calculation is done in the class. But again, it breaks if we do a capture. And now we can see if I can type without looking at the screen. And if I now try to capture X, that breaks down, and it should tell you on the right side. Cannot add shadows, something else. I don't want to do that as well. Make it more clear. I'm sorry, this is really hard with these screens. And it says that our lambda is not a structural type because of this capture. And I find it unfortunate that this is not working. Maybe this can be changed in the future. So I would find it really cool if we could have structs and classes with private data members as non-type template parameters, because it would make these things possible. And I'm honest here, I don't know why this is not possible at the moment, or why the design has been chosen in this way, but maybe someone in the audience can elaborate on that later. That would be really cool if someone knows why. How much time do I have? Okay, another application, for example, is we can use non-type template parameters to create strong types or unit-like types. So before that, most units libraries or strong type libraries are designed in a way that you use tags. So you create an empty struct, for example, called meter, and put that to a class which is a strong type, which implements a lot of arithmetic operations on that. And then you have like a strong type for that, a lot of libraries around there for that. And it's a good design, yeah. Tags are cool, tag classes, but you can construct now compile time strings, which you can pass as a non-type template parameter, which can look in a very simple fashion like this. So we start here something with a struct called string literal, which can be constructed from a string or a character literal, which stores all the data in a public array. And this kind of looks strange. What do I want to do with that? And the cool thing is, this is something I can use as a non-type template parameter in a struct called strong type, which stores also a value, and it implements some numerical operations like an add. And with that, I can construct strong types like a meter type or a kilometer type, which are different from one another, and I don't have to use tag classes here. I can just use these string literals here to construct that. And in the end, I can add 5 and 15 meter, but I cannot if I do kilometer here now. I cannot add that because that's not the same type. And this is something really cool. And if you want to see applications of that, you can see that in some strong type libraries or units libraries already. It pretty much amazed me when I saw that the first time. But I'm easy to amaze, so might be different for you. Another thing which you can do is you can construct like a ratio as a non-type template parameter. So as you know, there's stud ratio in the standard library, which is designed as a type template parameter and uses template metaprogramming to do calculations. But with const_expr functions and the new non-type template parameter things, you can construct that as a non-type template parameter, which is also useful, for example, if you're writing a units library And if you want to see that applied, you can have a look at the MP units library from Mateusz Pusch. And he uses all this stuff extensively in there. And I have just a short example here of how it can look like. And I will not go through the complete example, but you can just build a struct with public members, numerator, denominator, a constructor for that, a normalization function to normalize the ratio, and then some operators like, for example, here, for adding two ratios. And then you are free to use that as non-type template parameters and use, for example, some addition here in the template parameter list. And this works out. And here is the definition of the new unit, which has our new ratio as a non-type template parameter. And this is also something I find really, really cool. You can have a look at the example on the slide later with the more functionality in it. And this could be really useful in practice, I guess. Yeah, questions about non-type template parameters? Yeah, in the back.
So I'm Jeff. I wrote the classes with non-type template parameters proposal. So to answer your question earlier about why it has to be public, the idea was that they get mangled into symbols as all of the combination of all their members. So originally the proposal was that they had to be comparable with a default generated comparison, such as they were considered equal if all the members were equal, and that was a recursive property, so it had to be basically down to primitive types. There were some issues with that, and it basically got replaced with saying, basically, if all your members are public, you have no salient, non-salient attributes. You can't, because everything's public, so we can just serialize that and treat the members as the value.
Yeah, maybe then I can ask you a question. Would you see the possibility to get lambdas with captures working as non-type template parameters in any way?
Maybe. I think their current lambdas are currently completely out because you're not syntactically allowed a lambda in template parameter. And GCC, I ran into issues with GCC doing that. Thanks for that. There was a proposal, basically an operator template, so the classes could specify a way of serializing themselves as a non-type template parameter. I don't know if it'll ever happen. It's a pretty heavyweight thing. It would probably need. Lambdas probably not.
Oh, I'm sorry to hear that, but
It's not something that's been thought about. I don't think it might be possible, but I don't think the current proposal would address lambdas because members aren't really physical.
yeah, thank you for the elaboration. It's good to have you here then. Yeah, second to the end would be templated lambdas, pretty short. So we already had generic lambdas with auto in it. X and Y are basically their own independent template parameters. This might be what you want. It might be not what you want. For example, here in a comparison. We can constrain it in C++20. So here, X and Y need to be integral types, but it's not required that X and Y are of the same type here. But we can do that with templated lambdas now. So just insert the template parameter list after the captures. And you can do something like that if you want. Yeah, might be useful for you, might not be useful for you. And of course, I can put concepts in there as well if I want to make it rather lengthy. Because lambdas should be short, maybe it's not that a good idea to put also concepts and requires clauses in there all the time, but you can if you want. And yeah, that would be an end of a very short chapter where I guess nobody has a lot of questions because this is like one thing, but I think it's a nice thing. And in the end, just wanted to say there are a lot of fewer places where you need stuff like type name X of these qualified names. This has gone away in a lot of places. So if I find my cursor again. you can see that in a lot of places where you would have to write type name before, you can just do it without that. That's also not very magically, but it's nice. Yeah. In C++17, the compiler was complaining a lot of time that you need to write type name there, so it already knows what you need to do or what you want to do. So now this has been gotten rid of, and this is really cool as well. Also, not the longest chapter, but basically in here for completion. And this is not what I want to do. This never happens during rehearsals, happens only live. I'm sorry. So this would be the end, and I like to have like a small wrap-up in the end. So if you can use C++20, use concepts, they're really cool, and I talked about them at length because they're really cool. Maybe you have applications for the new NTTP stuff in your code. You can use templated lambdas if you want, and you don't have to write type name that much anymore. That's also cool. This is the 4 key points if you want at the end. And then I would say thank you for listening to me, and I will be here for the rest of the time for questions. We have a couple of minutes. So if you have questions, make yourself visible or audible. This does not seem to be the case. Then again, thank you for listening to me. I will be here until tomorrow. You can talk to me if you want. And have a nice day and nice rest of the conference, everybody.